Hello to all of you students out there who are joining us for this year's virtual Day in the Park. I am Greg Blaney, the director of the NASA IV&V program located in Fairmont, West Virginia. This event is one I look forward to every year because it gives me, the NASA team, and the other partners here in the park an opportunity to tell you how you too can become an employee of NASA or one of these awesome companies or organizations in the area. First, let me tell you a little bit about me. I was born in Morgantown, but lived just across the border in Pennsylvania. My wife and I left the area to go to college, never expecting to be able to return. After a few other jobs in other places, I got a job for the Bendix Field Engineering Corporation at the Goddard Space Flight Center as a contractor to NASA. I started at the very bottom of the ladder, but eventually worked my way up and switched over to being a NASA employee. And I've been working for NASA ever since. I wasn't at the top of my class in high school, actually just, maybe average, but my parents had instilled in me a strong work ethic, which was to do whatever needed to be done to make the company successful, the people that I worked for, and then look for the next thing that needed to be done. As my parents and in-laws got older, my wife and I were traveling back and forth to this area often to take care of them. We never thought we'd be able to move back to the area since I loved working for NASA. However, when the NASA IV&V program was established in Fairmont, West Virginia, I had that opportunity to come back and work for NASA, and so I did in 1996. Now, each of you has the opportunity to find a great, well-paying job right here in West Virginia if you want it and if you pursue it. This Day in the Park event is an awesome way to start figuring out what you are interested in and where you can apply those interests as a job right here in West Virginia if you want. And I'm focusing on if you want and if you pursue it. A lot of it is up to you. Now is the time to start building your career. Focus on learning while you're in school. Take advantage of events at school, robotics competitions, internships, day in the parks, just like this one. I really didn't do that when I was your age, but I was still able to have an exciting career at NASA, getting to work with astronauts and visit awesome NASA facilities around the country. Now, my career is ending because I'm retiring at the end of the year after a wonderful career with NASA. But NASA is still doing a lot of exciting things, and they will need good employees once you get out of school. So I leave you with this thought. You will be 22 years old someday. So you can decide now to be ready for a great career, or you can wait until you're 22. Or you can start thinking about a career now and decide whether you're going to be prepared for it or not. So I'm here to encourage you, and I strongly suggest you start thinking about that career because you'll be a lot better off if you do. So I hope you enjoy this day in the park. I hope you find it as a way to stimulate your interest in an area, and I really hope you can come and work for NASA someday. Thank you very much and have a great day.
Good morning, everybody, and as Director Blaney said, welcome to Day in the Park 2021. We have 3 days of exciting content lined up for you, and our first speaker comes to us from the Johns Hopkins Applied Physics Lab. This is Doug Adams, and he's going to talk to you about the Dragonfly mission, which aims to put a semi-autonomous drone on the surface of Titan. Take it away, Doug.
Hello, my name is Doug Adams, and I'm the Dragonfly Flight System Architect. And I'm here today to discuss with you the flight of Dragonfly on the surface of Titan, which is the largest moon of Saturn. And it's an organic world, an ocean world, and we're very excited about this mission, and I'm very excited to share it with you today. One thing I want to point out that's very fun is that this picture on the right is a real image. It was taken by the Cassini spacecraft. And in that image, after we process it, we filter the light, we're able to see the landing site where Dragonfly is going to go. It's a fascinating image, and it's a beautiful one. And again, we're very excited to go there. And by we, I mean the team. There's a team of people that it takes to make Dragonfly work. And there's a picture of some of us in the lower right, but there are many more. And maybe one day some of you can be a part of that team. We look forward to having you join us. So what is Titan and why is it so compelling for us? The science we're interested in at Titan is prebiotic science. So life here on Earth has overprinted our planet. Our biosphere contains life everywhere. So we don't know what our planet looked like before life was there. And at Titan, we find a chemical time machine or a time capsule of what the universe looked like, in particular, our solar system looked like 4 billion years ago. And it provides key chemical puzzle pieces to what may have been the beginnings of life here on Earth. And that makes it a fascinating place for us to visit, to understand our chemical origins, ironically, by leaving Earth and going to another planetary body. Titan is an ocean world. It has an outer ice shell and a global surface ocean, and it has a silicate core, a rocky core that's about 4,000 kilometers in diameter that's coated by an ice layer. But there is a liquid ocean under the ice layer. We will be landing on that outer shell, basically like an eggshell around the planet. And that will be where our Dragonfly mission takes place. A little bit more about Titan. It's a fascinating place, and I'll show you some more in a second. It's about 1.5 times the size of Earth's moon and has only 1/7 of Earth's gravity, a little less than Earth's moon, which has 1/6 Earth's gravity. Its surface density is very high. The atmospheric surface density is more than 4 times the density of Earth's atmosphere. But even more impressive is the atmosphere thickness. It's 10 times the height of Earth's and Mars' atmosphere and has 10 times the column density, which means that over a patch of ground on Titan, there's 10 times more air above it than here on Earth. But that comes at a price, which is that it's very cold. It's very far from the sun, and it's nearly liquid nitrogen temperatures. You see there at minus 290 Fahrenheit. For perspective, about the coldest place that's ever been, or coldest temperature that's ever been recorded on Earth is in Antarctica, and it's about minus 110 degrees Fahrenheit. So it's much, much colder on Titan, very cold place. Just a couple, these are the only equations in the whole presentation, which explains why we're so excited and why we're flying a rotorcraft at Titan, and we'll see that in a second. But the power that it takes to hover is proportional to the weight, mass times gravity, to the 3/2 or 1.5, divided by the square root of 2 rho a, so divided by the square root of the density times the area of the disk. And what that means is that on Titan, we can fly with 2.5% the power that it takes to fly here on Earth. So it's much, much, much easier to fly on Titan. And a rotorcraft is an excellent way to explore. So that's how we ended up with our Dragonfly mission. Again, to put Titan in perspective, it's a very large moon. It's actually larger than the planet Mercury. And if it were orbiting the sun, it would be a planet in and of itself and not just a moon of Saturn. And it has the second highest surface pressure of any rocky body behind only Venus, which of course has a massively thick atmosphere. It takes about 29.5 years for Saturn to go around the sun. So Titan's year is, a year on Titan is 29.5 Earth years. It has a similar axis tilt to Earth's, which is kind of fun, but Titan's day is 16 Earth days long. In other words, it's in what's called tidal lock. So it's like Earth's moon, you know, the man and the moon, where if you look at the moon, it always kind of looks the same. Well, Titan is the same side of Titan always faces Saturn. So its day is 16 Earth days long, which is also its orbit. And as I said, it is really far away. So here you can see Earth is at 1 AU, that's an astronomical unit, which is about 93 million miles. Venus is about 0.7, Mars is 1.5, Jupiter's at 5, but Saturn, which is where Titan is way out at 9 AU, or close to 1 billion miles from Earth when Earth is on the opposite side of the sun. So it takes a long time to communicate with our probe when it's on the surface. It takes about 70 minutes one-way light time, or about 140 minutes round-trip light time, just to get a signal to and from the lander. So it has to have autonomous capability. It has to be able to fly itself around and make decisions on its own. And there's an interesting history to Titan. So this is a photograph that was taken of Titan in 1981 when I was a kid, not that much different than your age right now. And you can see all we saw was this big cue ball, big kind of light tan sphere in space. And we didn't really know much about it underneath. And we were quite interested, of course. And so in the late 90s, a spacecraft called Cassini with a probe provided by the European Space Agency called Huygens was built. And this was a huge spacecraft. This was a flagship spacecraft. You can see the high gain antenna, the large dish on the top of the spacecraft on the left is 13 feet diameter. And for perspective, you can see a desk in the lower left. You see it's just an enormous spacecraft. And the people next to the probe on the right, even the probe makes people look small. So Cassini was a wonderful mission. It launched in 97 and spent 13 years orbiting Saturn, and it did a total of 126 Titan flybys. And what we learned from those Titan flybys is we learned what Titan looked like underneath the clouds, because Cassini brought along some very special instruments. And it also brought the Huygens probe, which on January 14th, 2005, made the first and only thus far landing on Titan and descended to the surface. And you can see the picture on the right here, the kind of tan or reddish tan colored picture of that it took from the surface and relayed the image to Cassini as Cassini flew by. For perspective, you can see a photograph taken on the moon that has a similar geometry to it. Those rocks that you see, we call those cobbles, and we believe that they're ice cobbles, liquid ice cobbles, and they're approximately the size of a large grapefruit, or maybe as big as a volleyball. So one of the things, as I mentioned, Cassini had some very special imaging capability, and it had, in particular, the capability to image in infrared. And what that does is it removes the veil that the atmosphere on Titan has and allows us to see the surface. And what we see, this is a Mercator projection of Titan, is a very interesting place. The kind of brown swath that you see around the belt, around the equator, we call that the equatorial dune C. And the place that we're going is a place called Selk Crater, which is shown here very near the center of the image, that is in the Shangri-La Dune Sea. That's part of the equatorial Dune Sea. That's an infrared image. This is a radar image, which is a little bit confusing, but you'll see in a second why we're so interested in radar. Radar is a very powerful way for us to inspect the surface and see what's on the surface, what kind of features are on the surface. And again, for reference, that is Selk Crater, and you'll see that later. That's our target of interest. So some of the things we see, I mentioned the organic dunes. These are organic dunes, meaning it's not silicon sand like you have here on Earth. It's hydrocarbon sand. You can think of it as soot, for instance, very heavy in hydrocarbons. But you see these linear dunes, linear dune features they're very beautiful. And this is in the equatorial regions. We also see channels. There's a methane cycle. So methane evaporates and condenses in the air and rains down on the surface the same way that water does here on Earth. And when it does that, it creates river channels and lakes and features that if you didn't know they were pictures of another world, you would say they could be here on Earth. They also have, as I mentioned, they have lakes. These are the North Polar lakes. And I mentioned clouds. If you look at the image on the right, you can see clouds moving. It's a time-lapse photograph or a series of photographs taken by Cassini. And you can see these little clouds maybe about near the middle. They're orbiting around or rotating around, not orbiting, but they're moving west to east around Titan. Fascinating place. So as I mentioned, we're going to Selt Crater, and the reason we're going to Selt Crater is that it in particular is very appealing from a science perspective. It turns out there's 3 basic ingredients that you need for life. Now, we don't expect to find life on Titan, but we're looking for the precursors to life. It's too cold on Titan for life to be there now. But the 3 ingredients you need are energy, which here on Earth is typically sunlight, which gives you photochemistry. You could also, as you know, there are ocean vents in the deep ocean that have chemical energy sources that the life there uses to sustain itself. So you need an energy source, you need organic material. As I discussed, the surface of Titan is coated in organics, owing to the fact that there's methane in the atmosphere that interacts with ultraviolet light. And then you need a liquid. On Earth, that liquid is water. And as I mentioned, there is ice on Titan's surface, and there's also methane. But this brings us to why we're interested in SELT, because as you can see in the diagram on the right, if you had an impact of something, and we don't know what it is that created SELT Crater, it could have been a comet, it could have been an asteroid, but there was something that hit the surface, and for a short time, it would have melted that surface, the ice surface, the subsurface. So in that short period of time, while it was liquid, you had aqueous chemistry, you had liquid water chemistry with hydrocarbons, prebiotic hydrocarbons interacting on the surface. And then that chemistry was frozen. And we're going to fly there and investigate that chemistry with our science instruments. And this is what we're going to take to Titan. This is the Dragonfly lander. It is an X8 octocopter. So there's 4 pairs of tandem contra-rotating rotors that allow us to fly around on the surface. And here's a little bit more about that copter. Of course, we have to get the copter to Titan, which means we have a spacecraft version. So it launches on top of a rocket, and we have a cruise stage and an atmospheric entry vehicle. We do a hypersonic entry, what's called a direct ballistic entry at Titan. And that entry vehicle, we shed the cruise stage, I'll show you a movie a little bit later, and enter the atmosphere and deploy a parachute and descend through the atmosphere in order to get to the surface. And then we have our final configuration on the surface where we've shed both the crew stage and the aeroshell, and we're left with just the lander. One thing I'll just mention quickly is that it is tricky to get an aircraft to Titan because you have to package that aircraft inside of an aeroshell, and that aeroshell has to fit inside of a fairing that goes on top of a rocket. So we're restricted on geometry. We can't just make it any shape that we want. We're limited by this circle that goes around us. And so you can see the rotors are tangent to that circle. They kind of go along this, they fit within that circle. And that's so that we can get the largest rotor separation that we can, which gives us better aerodynamics. But we're limited again because we can't necessarily do exactly what we would want to do aerodynamically. So there's a compromise in that design. And you can see on the right, the rotors are even tilted a little bit in towards the lander at the top as opposed to the bottom in order to get us even more capability when we fly on Titan. So a little bit more about the lander. We are planning to be powered by a MMRTG, which is a multi-mission radioisotope thermoelectric generator. You can think of it as a nuclear battery. It's basically like a very large battery that's powered by the radioactive decay of plutonium-238. And we do direct Earth communication. Unlike Mars, there are no, or Earth for that matter, there are no orbiting assets that we can use to relay signals to Earth. We have to use an antenna, which you can see on the right. The HGA is the high gain antenna. That's about 34 inches in diameter. We use that to transmit signals directly to Earth. The lander is very big. It's about 5 feet tall, about 12 feet wide, and about 12 feet long. So it's not the kind of thing that you would find in a hobby store. This is more like the size of a car, like a small car, and it weighs about the same as a small car too. The last thing I'll mention on the right here is the panorama cameras, which are on top of the high gain antenna. We plan to use those to take panorama mosaics that we can downlink to Earth, so that in the future, in the 2030s, we'll be able to put on virtual reality glasses and stand and look around as if we're standing on the surface of Titan. We'll have an ability to record sound too, so it'll be just like you're there in person, virtually, of course. Quickly on the instruments, I won't go through all of these in detail, but we have a mass spectrometer called DRAMS. That is used to, you'll see some of that in a video in a second. That's used to do chemical analysis of the surface. And it's accompanied by a drill called Draco that's used to collect the samples that go into the instrument. There's a gamma ray and neutron spectrometer that kind of gives us bulk chemistry. There's a meteorologic package called DRAGMET, that also does some geophysics. And then of course we have cameras, lots and lots of cameras. There's 8 science cameras and 2 engineering cameras that are called navigation cameras that we use to fly. And one of the reasons that we picked, now, so you remember I showed you the points on the surface that were in those little yellow circles. One of the reasons that we picked Silk Crater, which you can see here in the center image, is that just beneath Silk Crater, you see this thing that looks kind of like a fingerprint. And those are the linear dunes. So there's an ejecta blanket around the crater, and that's kind of a hazardous area, but those dunes are a friendly area. And we have an analog here on Earth that you can see on the right. There's kind of an aerial image and a surface image of the Namib, which is a desert in Southwest Africa. It's in Namibia. And you can look that up on Google Earth, check it out and zoom in on it. And it's a rare kind of desert on Earth where the desert goes right up to the ocean. And as a result, the wind blows off the ocean and creates these very large linear dunes that are a very good analog to what's on Titan. And this is an image that we commissioned to be taken by a satellite so that we can get stereo image and generate some representative digital terrain maps that we could use to develop the lander. And you can see the Namib looks very much like what you might expect. In fact, in a radar sense, it looks almost exactly like what you see in the Cassini radar that's shown on the left here. So we're very happy that we have this resource here on Earth to help us develop the lander. Again, these are silicon sands, but the same, as opposed to hydrocarbon sands, but same basic features in terms of geometry. So how do we get around on Titan? And this is kind of a little bit of cleverness here. We always want to know where we're going. We don't want the lander to have to make too many decisions on its own. So once we make the first landing, of course, the lander has to do the first landing all by itself because we just don't know where it's going to go. But once the lander's on the surface, and that's in the green circle on the left, the first thing it does is it takes off, scouts a new potential landing site, which is the blue, and then it flies back to the green. So the idea is that it starts in a place that it knows, which is the green. It flies to a new place, but doesn't land. It just flies around and takes pictures, and it comes back and lands in the green area, which it knows. And then from then on, what it does is what we call a leapfrog, where it'll take off. Again, it knows the green, and it now has pictures of the blue. And we tell it where in the blue we want to land. We say, go to this particular place and put your feet down there. But what the lander does is it flies over that landing site. It flies past it to the purple on the right, where it scouts a new candidate landing site, takes more images of those, and flies back to the blue. So it's 2 steps forward, 1 step back. And this way, we're always able to land at a landing site that we've pre-selected here on Earth so that we know that it's going to be safe. And it minimizes the risk for the lander. So that we use this leapfrog strategy to get around on Titan and make progress from our initial landing site to Silk Crater. And we do that with a very carefully selected set of instruments. We have Forward science cameras, which we use in flight to take pictures for scientific reasons and downlink them. As I mentioned, there are navigation cameras. They're black and white cameras, what we call panchromatic cameras. They're basically grayscale cameras, and we do that for sensitivity and ease of process. And then there's some LiDARs, which is like, it's a laser radar kind of thing, a LiDAR, if you want to think of it that way. And those are used to inspect the terrain. It kind of gives us a texture of the terrain, and you'll see that in a second. And then, of course, there's microimagers and down science cameras. We don't use the microimagers in flight, but we do take pictures with the down science cameras while we're flying too. So this is how we get around on Titan. It's kind of an interesting trick. So these are those panchromatic images I mentioned that we get from the nav cams, and they're black and white. And what we do is we take an image. The current image is the one in the upper left, and we compare that image to a previous image. It's either one that we took a second ago, or it's one that we took on the previous flight that we call a breadcrumb. And those breadcrumbs are the green squares that you see in the upper right. And the objective here is that we're trying to fly along the green square so we can fly back to the landing site that we wanted to, or fly to the landing site that we had scouted. And in this case, so what it does is it takes the current image and it compares that image when it's resampled to look like the previous image. It does a mathematical comparison, which you see is in the correlation matrix on the bottom. And if it scores well in that correlation matrix, it's included in our navigation, and we're able to fly. So the fun thing about that is that the blue in the upper right is where the lander thinks it is, and it thinks it's flying right over these images because, in fact, it is flying right over the images. The black is where the lander actually is, but we don't care about the fact that the black is misaligned from the blue, because what we want to do is we want to be able to fly to where the images were, because we're flying, we told it to go fly to a place in an image. So the fact that the images aren't exactly where we thought they were doesn't matter. What matters is the lander has to be able to find the images and fly to them, which is kind of a neat little trick that we play when we make this fly around on the surface. So as I mentioned, we also use the LiDAR to collect information about the surface and to help us find a safe landing site. And in this case, we define a safe landing site as having an average slope of 10 degrees or less. It could be, you see the ideal site on the left would be perfectly flat. And then on the right, you have a 10-degree slope. And of course, there could also be hazards. And we define a hazard as being something that is at or below a 1/4 meter radius or a 1/2 meter diameter hemisphere. That we jokingly call that a NASA standard rock. And the lander is designed to be capable, the LiDAR is capable of detecting anything that's bigger than a 1/4 meter radius and rejecting that landing site. And it does it this way. So on the left, I'll give you a quick intro. On the left is the truth map, and it includes some rocks. And then what happens is as we fly over it, the LiDAR scans that surface and provides us with a measured elevation, deviation, and slope map after processing. So you see the raw images, raw LiDAR images on the left. And then from those, we get ranked landing sites. On the right, you have our number 1, 2, and 3 ranked sites. And you can see those get adjusted as we fly along. As one scores better, it'll skip over the next one, and this will play one more time. So you see there's the number 1 landing site. It says, "Ooh, this is the best place I've seen so far." And then it decides, "Oh, well, no, there's a better landing site, a 2 and a 3. And it's reporting these to what we call a flight mode manager, which is kind of the brains of the operation. And it's deciding which landing site to go to. So after it's flown, in this case, it's about 100 meters. It says, "Okay, I found my best landing site," and it'll turn around and land there. And this is the product of that effort based on our simulated terrain. And you can see that it found this, the number 1 site has a very large radius that's free from large hazards, and it also has a low slope. So it's a happy place for our lander to go and land. And the LiDAR has done its job, and so has the system, and it'll fly there. And then we get to continue on with the mission. So the next thing I have is a little movie, and I'll talk you through this. This shows a little bit of the development that we did on Dragonfly, and also a little look to the future. So unlike most spacecraft, Dragonfly is an aerodynamic vehicle. We have to fly through the air. And what you see here is computational fluid dynamics that estimate the performance of the rotorcraft as we fly. And we also did some testing. So this, again, these are contra-rotating. You can see they spin in opposite directions. rotors with some load cells on them, and we spun them up and we sprayed them with liquid nitrogen. Remember, I said it's almost liquid nitrogen temperatures on Titan. And then we went out in the field with you see a little white box on the bottom of this drone. This happens to be a quadcopter, not an octocopter. But that was what we called the drone box, kind of a silly name. And you see the snow on the ground. We got all excited, like, oh, it's like Titan, it'll have snow. Let's go fly, fly, fly. Turned out that wasn't such a good thing. But here is the vomit-inducing video on the right of what that copter saw as it flew around, and the little purple dots on the left are how it's navigating it, and it used that imagery to navigate itself out and back to the landing site. And no discussion is complete without a rocket. You'll see a bird that has a really exciting morning. This happens to be the Mars Science Laboratory Curiosity rover launch. We don't know yet what rocket we're going to be on, but we know we're going to be on a rocket. And rocket launches are always fun. Here's the solids peeling off, and now we're in space, and we're going to skip the orbit. And this is our Titan arrival. We're spin stabilized, just like a gyroscope. And we come into the atmosphere spin stabilized. Again, the atmosphere, about 1,270 kilometers. We hit about 7.3 kilometers per second. And that's atmospheric entry. We deploy a drogue chute about 6 minutes later at 135 kilometers, which is above the height of Earth's atmosphere. That's how thick the atmosphere is. It's crazy. And then we fall for about 90 minutes to about 4 kilometers above the surface, where we deploy a main parachute. We drop the heat shield shortly after we deploy the main, exposing the lander to the atmosphere. And then we get the lander ready to fly. And one of the things we do is we spin the rotors to stop the spin rate. And once we're ready to fly at about 1.2 kilometers above the surface, we do a mid-air deployment, and away we go. We fly. We're now in powered flight. We've shed all that stuff that we needed to get through space, and we're looking for a landing site, because we don't know where that landing site is. So we do reconnaissance. We fly around on the surface looking for the best place that we can find to land. And when we find it, we put our feet on the ground and radio home, tell everybody at home that they can breathe again. We're on the surface, and we all smile and we wave. So here is the Draco system that pulls samples into the, and you can see this is a kind of an hanger queen or an iron bird that we built to do this. We have a rotary drill and a pneumatic system, the same as a vacuum, basically like a vacuum cleaner. And and there's your vacuum cleaner motor. It pulls air and the tailings up through this pneumatic system. We tested this on some ice, that's water ice at cryogenic temperatures, which is as hard as concrete. Just ran the gamut, ran the system through tests to show that we can grind up that surface and collect the material. And the beautiful thing about Dragonfly is that when we're all done at one landing site, we shut we close everything up, and then we can fly off and go to the next landing site. It's a terrific mission, and I hope you enjoyed the presentation. Again, the mission is called Dragonfly. You can look it up on the internet at dragonfly.jhuapl.edu. My name is Doug Adams. I thank you for your time, and I wish you the best of luck in your studies. Thanks.
Welcome back, everybody. Our next presenter is Nick Owe, a doctoral student at WVU, pursuing a doctoral degree in aerospace engineering. Take it away, Nick.
What's up? I'm Nick. I'm a PhD student at West Virginia University, and I work on robots. Specifically, I work on the way that robots think and make decisions autonomously. I do this for all kinds of robots, including future Mars rovers, and robots that help pollinate the plants that make our food here on Earth. Now, don't get me wrong, I love working on robots and all these things are really cool, but a person has to do something other than their job and have hobbies, right? So, in addition to robots, the other thing that I do is I build Tesla coils and other crazy contraptions involving high voltage electricity. I actually have a YouTube channel about this called Coil Labs. So I guess I'm really the robots and high voltage lightning guy. But the NASA folks invited me here to talk about robots, not Tesla coils. So I guess I gotta talk about my day job. That's alright, robots are really cool too. Anyway, back to autonomous robot decision making. What does that mean? Well, think about this. Imagine you're a robot on another planet. You get sent instructions from the humans back on Earth telling you to do things like, go here, look at this rock, take this soil sample, things like that. How do you know how to do each of these tasks? Well, all you have in your mind is the programming that was given to you by the human engineers. Each of those tasks, drive here, take a soil sample, whatever, breaks down into a list of actions that you have to perform in a sequence. Think about it this way. If you play a team sport like soccer, basketball, football, whatever, you probably have a playbook that tells you how to run each play that you've learned how to do in practice. The robot's programming is essentially just that. It's a playbook that tells the robot how to perform each task that it's commanded to do. The problem is, that playbook is all the robot knows. It really doesn't have any way to improvise or come up with ways to do things outside of what it was specifically programmed to do. At least, not with existing methods. That's where what I'm working on comes in. So, what are the existing ways that robots make decisions? Well, the way most of them work is by using something that we call a state machine. This is just a concept that exists in the robot's programming, but basically what it means is it's in some state that means like at the crater, and then it takes an action that says drive to this location, and then once it gets there, it's in a new state called at the big rock, or something like that. Then it keeps doing that kind of thing over and over again to complete all of the tasks that it needs to do its mission. Now this works fine, as long as you can be sure that when the robot takes an action, that the outcome is predictable, and that every possibility that can happen is covered by every one of the states that the robot can possibly be in. The problem is, most real-world situations involve some element of chance, things that are random, not predictable. And also, in real-world environments, it is impossible to account for every single possibility that can happen to the robot. There are always going to be really specific things that can happen to the robot that cause it to get stuck and need human help in order to figure out what to do next. There's no way to account for every single possible thing that can go wrong. There's just no way. There are too many. Let me show you what I mean. So, one of the coolest things I ever worked on was something called the NASA Sample Return Robot Centennial Challenge. We built a robot that had to search a large outdoor area, find different samples, pick them up, and bring them back to its home base. This is similar to what the upcoming Mars Sample Return rover mission will have to do. And it had to do all of this fully autonomously, no human sending it commands or telling it what to do. This was a really hard thing to do, but our team from WVU, with the robot we built named Cataglyphus, was the only team to ever successfully complete this challenge. And by doing so, we won over $850,000. So, of course, there were a lot of different things needed to make Cataglyphus work, but the way it made decisions about how to complete its mission was basically just what I said before, a state machine. It had to decide what areas to search for samples, then once it got there, how to search for them, and then if it spots one, how to approach it to try to pick it up, and then confirm that it actually picked up a sample, and then finally go home and drop it off on the starting platform. And repeat all of this again until all the samples are found or the mission time runs out. It should work, right? Well, it did. Mostly. We spent weeks and weeks outside testing the robot under all kinds of different conditions, trying to find situations where the state machine would fail and make the robot do something wrong or get into a situation that it didn't know how to get out of. Most of the time, it would do what we expected. But sometimes it would run into a situation that we didn't anticipate and run into a problem that it didn't know how to solve. And that's exactly what we were looking for with all of that testing. Conditions that we could model as the human designers writing the software and then specific logic that we could add to the state machine in order to handle that particular failure mode. The problem is you could account for hundreds of failure modes like that, but there are probably still thousands of other ones out there that you never even thought of. And that's exactly what happened with our robot Cataglyphus in the final challenge. In the last few minutes before time was up, the robot spotted a sample near the edge of the field. It drove over and tried to approach it, but when it got close to take another picture, it ended up that the robot's own shadow, just a tiny little piece of it, blocked the sample on the ground, and the robot's computer vision algorithms didn't recognize that that was the sample it was looking for because of the shadow. So then, the robot did exactly what we told it to do. If you couldn't see the sample, drive around and try to approach it from a different direction in order to get a different vantage point. But then, when it did that, the obstacle avoidance sensors didn't pick up this tiny little metal plaque sticking up out of the ground, and the robot ran right into that and got stuck and couldn't move anymore. We never picked up that last sample, and the time ran out. Of all the crazy failure modes that we encountered during testing and added specific logic to the state machine to handle, we never saw this particular failure mode. So the robot didn't have any pre-programmed way to know how to handle this. Now, don't get me wrong. We still completed the challenge and did really well and won a ton of money. But if the robot had picked up that one last sample, we would have won $1.5 million instead of just $850,000. Anyway, here's the point. No matter what you do, there's no way you can anticipate every single way that the real world can make the robot fail. Normal state machines work fine for very constrained environments like laboratories and factories, where all of the uncertainties around the robot can be controlled and the environment can be catered to the robot's limitations. But out in the real world, either here on Earth or on another planet like Mars, there is no way to assume away all of the possible unknown factors. That means we need to rethink the way that we design autonomous robot decision-making if we want them to be reliable in the real world. So remember what I said earlier. State machines work fine as long as every outcome is predictable and not random, and that every possible outcome is known ahead of time. Well, in terms of things being random, there actually is already a lot of really cool work that has been done and is still being done to account for this. We call this decision-making under uncertainty, and this is a huge area of research in robotics. Now, I won't get into the details here, but let's just say that there are a lot of people way smarter than me who are working on this, and there are a lot of really good ways to handle uncertainty. The thing that there doesn't seem to be as many people working on, though, is the not every possibility specifically accounted for part. And that's where what I work on comes in. So the question is, how do we make a robot that is capable of dealing with unknowns? Well, some people try to solve this problem using machine learning. There have been a lot of great things that come out of this, but it's still not quite enough, and to me, it's still not really addressing the real fundamental problem. These machine learning approaches are saying, okay, if the robot can't be given a detailed model of its environment by the humans, then let's let the robot learn the model of its environment by collecting data. Here's the problem with that, though. You need training data about every single possible aspect of what can happen to the robot in order for this to be reliable. You're still assuming that you can expose the robot to every possible situation it's going to encounter, and that you can collect data about all of those situations, and that by doing that, that you have a complete model that describes everything. Then, using traditional decision-making techniques, you can make rational decisions by assuming that the model you have is complete and accurate. Even if you collect tons of training data, though, I'm still certain that there is no way that you will account for every single possibility of ways that the robot can fail. So what can we do then? How can robots make decisions if they can't know every possible situation that can happen? Well, there are some interesting ideas coming out of other areas of robotics research that might help us figure out how to do this. And one of those is robotic swarms, which are a bunch of robots all operating independently, but working together to complete a task. You've actually probably seen some robotic swarms already, like these drones that can fly in formations and make really cool shapes. These swarms aren't that smart, they're just following some simple instructions, but they have some really cool properties that we can use to make them do more complex things. One of the most important ones is that each robot in the swarm, each swarm agent, as we say, doesn't need to have full knowledge of all of the other robots in the swarm. It's just programmed with some really simple logic that tells it how to interact with the other swarm agents nearby. Not the whole swarm, just its neighbors. We call these local interactions, and if we design them correctly, we can get behaviors out of the entire swarm that are way more complex than anything the individual robots are programmed to do. Like these flying drone swarms. Say you want the swarm of drones to make a sphere. You don't need to program each drone with full knowledge of how to make the shape of a sphere. You just give each drone some really simple rules telling it how to position itself relative to its neighbors. And because every drone in the swarm has these rules, the interactions between all of them collectively result in way more complex behaviors than any individual drone knows how to do. We call this an emergent behavior, something that is not directly programmed into any of the individual robots' code, but is more complex than anything that they could do individually. This is kind of similar to the way that a lot of insects behave, like ant colonies. Individual ants can't do a whole lot, and each one isn't that smart, but when they interact with each other, they indirectly exchange information about the problem they're trying to solve. And when they cooperate and work together, they're able to do things that are way more complex than any individual ones can do. So, when they work together as a swarm, they are more capable than the sum of the individuals. So back to robot decision making. If we can make swarms of robots that have very simple rules about how they interact with each other and about their environment, something that's very achievable to do as a human programmer where you're not trying to cover every possibility, then a lot of the gaps in their knowledge that aren't accounted for can be handled through these local interactions and emergent behaviors that come about as a result. At least, that's the idea. Imagine, instead of one robot searching for samples, we had a whole swarm of robots searching for samples, and as they interact with each other, they can influence each other and help make the swarm better overall. If I'm one robot and I see another robot coming home with a sample, then I think, okay, whatever it's doing must be successful. Maybe I should imitate what it's doing and go search over there. Maybe I'll be more successful. There's no guarantee that these emergent behaviors are always going to help, but it at least gives the robot a chance to do something that's more complex than it could on its own, and that doesn't need to have a complete, accurate model of everything that's going on beforehand. We still have a long way to go on this kind of research, but we're actually testing these kinds of things right now in computer simulations. Then, once we see some promising results, we'll move on to trying this on real robots in the real world. We're also thinking about ways to transfer this emergent behavior property of swarms back to single robots, because sometimes having a bunch of robots isn't beneficial. Having multiple robots instead of one costs more, or maybe there's not enough space where you're trying to have them operate, or things like that. But the idea is that maybe a single robot imagining that it's a part of a swarm and thinking that it's interacting with other virtual swarm agents will result in these kinds of emergent behaviors on a single robot. We still have a lot to do to figure out stuff like this, but maybe robots having imaginary friends is actually a good thing. Anyway, I hope you all enjoyed this little look into how robots think and make decisions. Maybe that's got you thinking about how you can get involved in robotics. And if so, well, you're in the right place. Thanks so much for listening. Oh, and one more thing before I go.
Welcome back, everybody. It's my pleasure to introduce our next speaker, John Holbrook. John is an AmeriCorps member from High Rocks, serving at the NASA IV&V Facilities Education Resource Center and working on their robotics expansion project, trying to get a robotics team at least in every county in the state. Take it away, John.
Hello, Day in the Park. I hope you've been enjoying our sessions so far today. And what we're going to do now is kind of a follow-along programming robotics activity. We're going to program our virtual robot in VexCode VR to behave like a robot vacuum. So VexCode VR is this website that allows us to write programs and run them on a virtual robot in kind of a simulated 3D world. So it can be a really great way to kind of play around with programming and robotics without needing to have a physical robot in front of you. If you have a device with you and you want to follow along as we're doing this, you're welcome to do that. VexCode VR is available at vr.vex.com, vr.vex.com. It runs in any web browser on pretty much any device, laptops, Chromebooks, tablets, and so on. If you don't have a device in front of you, that's fine too. You can always play around with VexCode VR later. Again, it runs in pretty much any web browser. And I want to look at, just before we get started here, some of the other resources that are available to get started and get some help and ideas for playing with VexCode VR. And those are these three buttons here in the top left of the screen: Tutorials, Activities, and Learn. If we click on Tutorials, then we get access to a number of kind of short videos that will show us how to do different things in VexCode VR. So driving the robot forward and backward, turning, creating my blocks, and so on. And if we click on any of these, we get a little video that we can play here right in VexCode that shows us how to do that thing. If we click on Activities, that'll take us to another web page on the Vex site that has a bunch of different activity kind of ideas. So there are lots of different kind of worlds that we can put the robot in, with different things we can interact with. There's like a maze, grids, and so on. So there's a bunch of different activity ideas here. We're going to do this one, Robot Vacuum, now, but there are lots of different ideas for things you can do in VexCode VR here. And then under Learn, if we click on that, we get also taken to another web page. And here there's a whole computer science curriculum that uses VexCode VR here. So if you want to learn more about computer science or teach yourself to program, this is one way to do that. Okay, so here we are in VexCode VR. If you have written any code in Scratch before, this will look pretty familiar. If not, the idea is basically that we have a bunch of blocks here on the left that do different things, drive the robot around, loops, questions, and so on. And we can drag those blocks from our palette here onto the canvas, where we can snap them together into stacks. So we started with this when started block, and I can snap a block onto that, and then snap another block onto that, and so on. And when we run the program, we'll start with the when started block, and we'll run the first block in the stack. And then once that's done, we'll run the second block in the stack, and so on and so on. So we can create these snap blocks together to create these programs. If I click up here on Playground, this is the virtual world that the robot is going to move around in. So if I click here, I can choose between any of these different worlds. There's all sorts of different environments that the robot could be in. We're going to stick with the grid map for our activity today, but there are lots of different worlds you can play around in. With these three buttons down in the bottom right, I can change the camera. So right now we have kind of the top-down camera. We can also get kind of, this is like if there were a camera on the robot looking forward, and we can get like a 3D camera here and look around and see the robot from different angles. Go back to the top-down here. And then these two buttons here, I can start the program, or I can reset everything back to the beginning. So I've written this little program here, and if I hit start, we'll see the robot's going to drive forward and then turn right and then drive forward again. So let's see that. Driving forward, turn right, drive forward. And I can stop. If I hit start again, then it'll do the same thing starting from where the robot was. And if I hit reset, then we go back to our start condition here with the robot in the bottom left. So we can write programs and then run them in this virtual environment. Okay, so our goal here is to program the robot to behave like a robot vacuum. So what do we mean by that? What does it mean to behave like a robot vacuum? Well, the goal of a robot vacuum, Roomba is the common name, or other brands are also available. The goal of a robot vacuum is to drive over every part of the room that it's in, right? You want to cover the whole area of the floor so that you can vacuum up everything. So our goal on this grid map is going to be to drive over every part of it, to drive over every square. So let's see if we can write a program to drive over every square of the grid map. I'll get rid of what we've written so far. So the first thing I'm going to do at the beginning of our program, I'm going to do a couple of things to make this a little easier. The first thing I'm going to do, I'm going to grab this block here in the purple looks category that says move robot pen down. The robot has like a little pen on it. You can kind of see it here. There's a pen in the middle of the robot. And if we move the pen down, oh, sorry, now you can see it. There's a pen in the middle of the robot. And if we move the robot pin down, then we'll be drawing a line as we're driving around. So we can see everywhere the robot has been and make sure that it's driven over every square. And then the second thing I'm going to do is I'm going to grab these two blocks that read set drive velocity and set turn velocity. This is just how fast the robot drives forward or turns when we ask it to do that. By default, it's at 50%, and I'm just going to set that to 100 just so things go a little faster here. So every program we write in this activity today is going to start with these three blocks, just so we can see things a little better. Okay, so we start here in the bottom left corner. I think probably the first thing we want to do if we just want to cover every square here is to drive forward so we get this whole column of squares. So that's what, 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. And I know from playing around with this earlier that each of these squares, each of these lines are 200 millimeters apart. So if we want to drive 9 squares in distance, that's going to be 200 times 9, or 1,800 millimeters. So I'm going to grab this block that says drive forward, and I'll just click here and type in 1800. So now we're going to drive forward 1,800 millimeters. So let's run that program just to make sure everything's working. Let's see, we're drawing the line there as we go. And yeah, that looks good. We've reached the middle of this top left square. So next, I think what we want to do is turn right and drive over here, and then turn right again and drive down this whole row. So we want to turn right 90 degrees. Then we'll be here facing to the right, so we want to drive forward just one square, just 200 millimeters. Then turn right another 90 degrees, and then we'll drive down this whole row, which will be 1,800 again. All right, so let's reset and we'll run that program. So up the first column, you can see as we're running the program, the block that's currently running will flash. So that's nice. We can kind of see where we are in our program. And here we are back here. So next, I think we'll turn left and drive over here, and then turn left so we can go up here. So I can turn left instead of right just by changing this if I click here. So now I'm turning left 90 degrees. drive forward another 200 millimeters, and turn left 90 degrees again. Now at this point, we're going to be here facing this way, and we want to drive up here, over, down, back, and then up again, over, down, back, and so on. So in other words, what we want to do from here is exactly the same thing we want to do from our start position here. And we want to do that a total of 5 times, right? Once to get these 2 columns, 2 for these 2, 3 for these 2, 4 for these 2, and then a 5th time for the last 2. So we have this kind of one set of movements that we've written we want to repeat 5 times. Now we could copy and paste each of these blocks 5 times to get a nice long stack that does everything we need. But we can make our code a little more efficient and save ourselves some time by just putting these blocks that we've already written in a loop. So I'm going to go down here to the control category, and I'm going to grab this block here that says repeat and then a number. And I'll drag that into my program. And if I drag it right here, you can see it's going to kind of expand so that all the movement blocks we've already written are inside of our loop, which is what we want. So now all the blocks that are in here, instead of just running once, we'll run this whole stack once. And then when we're done, we'll go back to the top of the stack and run it a second time, and so on, however many times we say. And so we want to repeat this number, or this little procedure 5 times. And so let's reset. And I'll make this a little bigger so we can see it run. And as we watch this run, we can see we've got the first set of steps here. So this is as far as we got last time. And now we're going to go back to the beginning of that stack and go up a second time, and so on until we get to that final square in the bottom right. Okay, so here we are. We've reached the bottom right square, and we actually kind of got caught up against the wall here because our robot tried to drive in to the next column, which doesn't exist. So that's maybe not quite what we intended, but we have you can see here by the pen line, we've gone over every square in our grid. So there we go. If we had a vacuum attached to our robot, we could have vacuumed the whole area of our room here. But if you've ever seen a robot vacuum running, it doesn't really take paths like this that are very straight and planned out and efficient. So why not? The reason that robot vacuums don't behave like this is that when we wrote this program, we wrote the program by looking at the specific room we were in and measuring distances and saying, okay, I think we can drive forward this distance, and then we'll turn and drive forward a little more, and so on and so on. So we wrote a program that was very efficient at covering all the areas of this room specifically. But we did that with the information about what size and shape this room was. We knew the shape of the room ahead of time. The software engineers who write code that runs on robot vacuums, their goal isn't just to write a program that will get the robot vacuum to cover the whole area of one room with a specific shape. If you're writing the software for a robot vacuum, you need to write a program that makes the robot vacuum cover the whole area of a wide variety of rooms that could be any shape. We don't know the shape of the room in advance when we're writing the program. So instead of measuring the robot, or measuring the room rather, and making it drive these specific distances, what we need to do to make our robot behave like a robot vacuum is we need to use the sensors on the robot to see the world around us in some way and to make decisions as we're moving around about what we should do next. So let's reset here. The robot has a bunch of different sensors on it that do different things, but the one we're going to use for this activity is the distance sensor. And that's this one on the front here, kind of pointing forward. And the distance sensor is looking at whatever the robot is pointing at, in this case, this far wall over here, and it's measuring how far away that thing is. And we can see what all the sensors are seeing, but in particular, we can see the distance sensor in this bar up here. So right now, that far wall all the way over there is 1,845 millimeters away. And that makes sense based on the program we wrote earlier, right? Because when we drove forward these 9 squares, we drove forward 1,800 millimeters, and we didn't quite hit the wall. So if the wall is 1,845 millimeters away, that seems like it checks out. So our procedure with using the distance sensor, let me just hide this for now, is going to be a little bit different. So I'm going to get rid of this drive code we wrote. So instead of driving forward some pre-measured amount, what we're going to do is we're going to drive forward and we're going to use the distance sensor to see if we're about to run into a wall. And if we are about to run into a wall, we'll stop, turn so that we're facing away from the wall, and then start driving forward again. And repeat that over and over until we've covered the whole area of the floor. So we're again going to have a loop here, but instead of repeating our action some fixed number of times, what we want to do is just repeat our action over and over until we say stop. So I'm going to grab the forever loop here, and the forever loop will just repeat whatever we put in it as many times as we let the program run. So this is going to be, all our movement code is going to be within this forever loop. So back up to the top category here, the drivetrain category, which will move our robot around. When we drove the robot before, we used this block here, drive forward for some number of millimeters. But again, what we want to do here is not drive the robot some fixed amount, but drive the robot until the sensor sees something. So instead of this block, we're going to use this block here, which just reads drive forward. And what that means is start driving forward and keep going until later in the program we say stop with this block here. So our program is going to look like start driving forward, then we'll have another block here that will tell us to wait until the distance sensor sees that we're about to run into the wall, and then after that we'll stop driving, and then we'll turn. So the wait block is going to be, again, down here under control, and it's this block here that reads wait until, and then we have this kind of pointy area here. This pointy area we're going to snap another block into that's going to tell us what we want to wait until. So in addition to creating stacks of blocks like this, we can kind of change what blocks do by snapping certain other blocks into them. And this area with the pointy ends means that what we're going to snap in here is a true or false value. So either the distance sensor sees that we are about to run into something and we should stop. It is true that we're about to run into something. Or false, we're not about to run into something and so we should keep going. So how are we going to decide if we're about to run into something? Well, what we have is a number, right? We have the distance that the distance sensor sees, and we're going to say that we are about to run into something if the distance that the distance sensor sees is less than some value. So if we're closer than some distance to the wall, then we're going to say, okay, we're about to run into this, let's stop and turn. So we want to take the number the distance sensor sees and ask, is it less than some other number? And we can do that with this block here, which is in the green operators category. It's the less than block. And here we have two of these areas where we can put in numbers. And we can type numbers in here, but we can also, this is also another area where we can drag other blocks in to get our number. So in the sensing category, I'm going to grab this block, which gets the distance that the distance sensor sees. You can see that snaps in here. And we're going to ask, is it less than some value? And I'm going to pick 120. So we're going to say if we're closer than 120 millimeters to the wall, then that means we should stop and turn. And of course, you can play around with other values and see what works better and what doesn't. So we've started driving forward. We're going to wait until we're closer than 120 millimeters to the wall. And once that's happened, then we can stop driving. And then the last step is going to be to turn. So let's say we're going to turn right, and I'll just pick a number here. Let's try 110 degrees. Okay, so let's see if we can see both our code and the robot running at the same time. There we go. So here's our code. Here is the robot running. I'll click play and let's see what happens. So we're driving forward, waiting until we get too close to the wall. Then we've turned 110 degrees. Now we're driving forward again. And here we go. So now we're kind of covering the wall, or sorry, covering various tiles in the room. And let's just let this run for a while and see how it does. Okay, so our program has been running now for just over 3 minutes. And you can see, we've covered a lot of the room. It's a lot of squares that we've driven over. But there's this big hole in the middle and a couple of smaller areas that we really haven't hit too. And if you look closely at what the robot is doing, you can see that it's got to a point in this kind of neat pattern we've created where it's basically repeating. So it's driving over places it's already driven over. And so because we're in this kind of cycle where we've already gone around once and now we're back to the beginning, it kind of looks like we're not ever going to reach this center part, right? Because we've already been everywhere we're going to be. We didn't get to the center. So we haven't succeeded in driving over the whole room here. We've made a cool pattern though. So, okay, maybe we can try a different angle. And, maybe after playing around and trying lots of different amounts to turn here, we can find one that works in this room and will get us across all the tiles. So we might be able to cover the whole room that way, but we're still depending on the shape of the room, right? If we did that, what we would have found is an angle that works in this particular square room. And the angle that works in a square room would not necessarily work in a room that was wider or that was a circle or that was some other shape. So we're still writing a program that is specific to the shape of each room. So we need to try something slightly different. What we need to introduce into the program is a bit of randomness. Rather than turning the same amount every time, let's try turning a random amount every time. And maybe that'll give us kind of the little bit of exploration that we need to get to these areas that we're not reaching under the current program. So I'll hit stop and hide this real quick. So randomness. Instead of turning right for 110 degrees every time we turn, we're going to try turning a random amount each time. And conveniently, down here in the operators category, there is a block that is called pick random. So we can just drag that in here. And then we need to set the smallest and largest possible amount that we can turn. So let's think about that for a minute. We probably don't want to turn a very small amount, right? If we're facing this wall and we turn right 1 or 2 or 5 or even 10 degrees, we're probably still going to be facing this wall and still about to run into it. So we want to make sure that we turn at least a large enough angle to get us away from the wall that we're facing. So let's say we want to turn at least 60 degrees. And again, that's just a number I'm picking. As you're following along, you can play around with different values for these and see how that changes, how the robot behaves. So we want to turn, I'm going to say at least 60 degrees. And we also don't want to turn too far, right? Because if we turn around the full 360 degrees, that's the same as not turning at all, basically, right? We'd still be facing the wall. So if we turned right, 350 degrees, then we would be basically almost back to where we were, and we wouldn't have turned away from the wall. So just like we want to make sure we turn far enough to face away from the wall, we also want to make sure we don't turn too far that we go all the way around and come back to facing the wall. So let's say we want to turn no more than 300 degrees. And again, you know, we can play around with these two numbers and see how changing them changes the behavior of our program. Okay, so this is kind of our third take. Instead of turning the same amount every time, we're going to turn a random amount. So let's run this program and see how it works. So here we go, starting out, and straight away we're going near the middle of the room, which is nice because we didn't really get that area very much before. Oh, now this is kind of interesting. We got caught on the wall there. The reason we got caught on the wall is because the distance sensor is, let's see if we can look at it here. You can see the distance sensor is in the middle of the robot, but there's also these two corners. And so if we're approaching the wall at a shallow enough angle, the corners will actually hit the wall before the distance sensor sees that we're lower than our threshold value. And so we'll kind of scooch along it. So we could change that. Here it goes again. Yeah, so we kind of got caught at the wall at the end there. We could change that by making our threshold larger. We could say we want to stop if we're closer than some smaller amount, but I don't think it's necessarily a bad thing if that happens a little, if we rub against the wall a tad. So you can see, you know, we're kind of driving a little bit randomly. We're not necessarily making the most efficient decisions. You know, here we just went back basically where we came. But if we let this run for long enough, and we'll see what that looks like in a minute, then we will, we'll see how much of the room we cover. So we're going to let this program run for a bit and come back and see how it does. Okay, so we've been running our program here for about 8 minutes, and you can see we've done a pretty good job of covering the whole area of the floor. There are definitely some parts that we've driven over more than others. You can see some places the line is darker. There are more of them closer together. That's just kind of how it goes when we're driving around a little randomly. But over time, we did get to all the areas at least some. So we've driven over the whole floor, and importantly for the idea that we're behaving like our robot vacuum here, we've driven over the whole floor, and there's nothing in our program that is specific to this particular room shape. So if we ran this program in a different shaped room, one that was more rectangular or even like a circle or something, we would still get over, you know, the whole area of the floor eventually. Unfortunately, I can't show you that because there are no other shapes of like worlds here in VEX Code VR. They're all squares with different things in them. There's a couple mazes, but there are no big open areas that aren't squares. So unfortunately, I can't show you that. But we can kind of see by looking at this program, hopefully we can convince ourselves that there's nothing specific to any particular shape of room here. So let me stop this program. So one last thing I want to kind of talk about is, you know, throughout all the programs we've written here, we've had the pen down and drawing a line of everywhere we've been. And you know, that's been useful to us writing the program because we can see where the robot's been. Have we achieved our goal of driving over every square? But one thing that's really interesting is that this kind of map that we've created of everywhere we've been can also be really useful to the robot. So a lot of robot vacuums actually will kind of keep track of where they're going as they're driving around like this. Obviously, they won't do it with a pen on the floor, but they'll have various different sensors in the motors that can track how far the wheels have turned and what direction they're facing and so on. And by using those sensors, they can kind of make a map like this internally of all the places they've been throughout their drive. And that's really useful because if you have this map, you can learn something about the shape of the room you're in, right? If I just showed you all these lines, even if you couldn't see the grid and the walls that the robot is in, if I just showed you these lines, you could probably guess that the robot is in a square room. And if you do this 2 or 3 times driving around randomly and look at all of those maps and they all look like squares, then you can be pretty sure that you're in a square room. And once you know that you're in a square room, or once you know what shape your room is in, then you can plan a shorter, faster, more efficient path that drives over all the area as quickly as possible, like we wrote at the beginning. So if we keep track of where we're going, we can make our robot more efficient over time. It can learn the shape of the room that it's in and learn to more efficiently drive around and vacuum up over the entire area. And this is a thing that some robot vacuums do, not all, but some of them can do this and plan these more efficient paths. And there's a term in robotics for this, which is SLAM, SLAM, and that stands for simultaneous localization and mapping. So simultaneous means kind of doing 2 things at once. Localization is this idea of figuring out where we are in the room right now using the distance sensor to say how far are we from the wall, do we need to stop and turn, or can we keep going? And then mapping is kind of keeping track of where we've been, making this kind of map of all the places we've driven and using that to learn about the shape of the environment we're in and planning more efficient paths later. Simultaneous localization and mapping is kind of the fancy term for what we're doing here. And it's really useful in a wide array of robotics applications. So not just robot vacuums, but also things like self-driving cars that are trying to learn more about the world around them kind of in real time, and lots of other really cool robots use SLAM to kind of get better at navigating around their environment. So I think it's really cool that just by driving around this room and drawing with a pen, we can kind of get an idea of a really useful and important technique that is being used in a whole bunch of really cool robots right now. Okay, so that's going to conclude our follow-along activity in VexCode VR. I hope you all found that interesting. And again, if you want to play around with this more, I would really encourage you to go to vr.vex.com. It can be really fun, and there's lots of cool stuff you can do programming your virtual robots there.
Hello, and we are going to be playing a quiz today. If you are watching us live, head on over to joinmyquiz.com and enter the game code that you see here in the little box that shows up on your device. While you are taking a moment to get logged in, I'm going to take you on a little tour of our Day in the Park website. Welcome, Turmeric Trunchbull. Okay, you can go to our website at dip.nasaivverc.org. Each day has its own sort of set of activities and things there. Today we're on robotics, so that's what we're going to look at. The live stream is here. You can watch that at any time. The recording will be there as well. We've got a little scratch game where you can program a robot to collect some samples. So you just click on or use your arrow keys to tell the robot what to do. Once you've got 3 commands in there, it goes for the sample. And then you can keep going from there. There may be some additional difficulty as you get through some levels. We've got NASA's Explore Mars, where you also program a rover. Some information on robots from ck12.org. Code.org course that's in here. And then this NASA educator guide shows you how to do an engineering activity using Spheros robots. And the NASA IV&V ERC now has a Spheros kit that teachers can be trained on and borrow. That's a great tie-in for there. If you happen to be watching this after the recording and can't participate in our live quiz, which will be starting in just a moment, the link right here will take you or your teacher to that quiz so you can play it either on your own or with a small group. And so let's go over here and get started. The live feed that you're watching now is on a 5-second delay. So once we start the quiz, you'll be able to see the question and the answers on your device before I start reading them, but I'm joining too just so that I can also read the questions off as we go. So you'll see them first on your phone, but I'll catch up with you eventually. All right, let's get started. What is a robot? The first answer, a machine that can complete any task. Green on my machine at least. A machine that is programmed to complete a certain task automatically. A machine that is made to look like a human. Or a machine that can do just about everything. Or a machine that can do just about everything. Right. Machine that is programmed to complete a certain task automatically. And I think if you're paying attention to Nick's presentation, he communicated that really well. The 4 types of jobs we like to use robots for are difficult, direct, ductile, and duplicitous, duplicate, dry, delicious, and dental, dangerous, delicate, dull, and dirty, dutiful, double, dreamy, and desperate. Right, and if you join us later at any time, you can head over to Join My Quiz and enter this number. It is floating on the bottom of the screen the whole time. We like to use robots for things that are difficult for humans to do, that would be dangerous, that are really repetitive and so kind of boring, or that it require a lot of precision that is difficult to do with a human hand. Love it. A washing machine is always a robot, is never a robot, or is sometimes a robot. Washing machines are robots. They are programmed to complete a particular task, and they do so autonomously once you set the dials and get them started, as long as you remember to put the soap in. The word robot comes from the Czech word robota, meaning forced labor, slaves, mechanical manipulator, or humanoid? Forced labor was the right answer, but those were all good choices. I like it. What is the name of a device used to detect what's going on outside the machine? Effector, microcontroller, sensor, or drive system drivetrain? Yeah, sensors are used to detect things outside of the machine. Isaac Asimov popularized the term robotics. What was his job? Our options are scientist, science fiction writer, inventor, or movie director. A science fiction writer, although he wrote other things as well. He wrote a Latin textbook that was used in my high school. Thankfully, I didn't take Latin. One of the first industrial robots was called Unimate and was used in a car factory, hospital, fancy hotel, or aluminum mine. A car factory. The car industry was one of the first to really heavily rely on robots. Why are sensors important to robots? Sensors allow them to move. Sensors let robots change their environment. Sensors give robots information about their environment. Sensors give robots directions for everything that they do. Nice. What makes a robot a robot? It can be programmed to do something else. It uses algorithms to work. It looks like a human. It has artificial intelligence. Robots can be programmed to do something else. What was the name of the first commercially available robotic vacuum cleaner? Trilobite, Roomba, Conga, or Salsa? It was the Trilobite. Roomba certainly cornered the market, but fun fact. Oh, yeah, we do want to end the quiz. Okay, congratulations to everyone who played. Turmeric Trench Bowl wins. And people did a very good job. All right, we are going to leave this quiz, and I think we have time to do another one. All right, let's do it. Just give me a second to get this started. We're going to do some science trivia today. All right. So same website, joinmyquiz.com, but a different game code, 309011. And I will have this on our website as well if you want to participate when you're not actively watching this broadcast. All right, let's get started. You can always see the code across the bottom of the screen down here. Please feel free to join. How many senses do humans have? Oh, 3, 5, 6, or 8 or more. And it is probably not the answer you learned in kindergarten. Yeah, we think of the normal 5, but then we also can sense pain. We can tell whether we're upside down or not. We know where our body is in space. There's a bunch of senses we have. It's pretty cool. On which of the following dates is the Eiffel Tower tallest? January 1st, August 18th, September 21st, or December 9th? And this sounds like a real weird question, I agree. But if you think about what the Eiffel Tower is made of, it might help you answer the question. August 18th is a hot day. The Eiffel Tower is made of metal. The metal expands, and so the Eiffel Tower is taller during the summer on hot days. The human body is over 50% water, oxygen, empty space, or all of the above. So how can it be all of the above? 50% and 50% and 50% is 150%. Well, most of the mass of a water molecule is oxygen. There's 2 hydrogen atoms, but they're very small. And atoms are mostly made of empty space. So technically, all answers are correct. Which planet in our solar system has an axis that is tilted by 98 degrees? Earth, Uranus, Jupiter, or Saturn? Anyone know Earth's axial tilt? About 23 degrees, I think. We are neck and neck for our first two positions. You are currently experiencing 1G, that's the force due to gravity. The International Space Station's maximum acceleration was 5G. How many Gs does a flea experience when jumping? 2 Gs, 5 Gs, 10 Gs, or 100 Gs? Gs. That's a lot. They're very small. Which animal has the best color vision? Humans, bumblebees, dogs, or mantis shrimp? So the amount of colors that you can see is determined by the types of cone cells in your eyes. Dogs have 2 different types of cones. They have the worst color vision of any of these animals here. Humans typically have 3, ones that are sensitive to red, to green, and to blue light. Bumblebees have a 4th cone, and most insects have a 4th cone that allows them to see ultraviolet light. So what they see when they look at a flower is totally different than when we see what we look at a flower, because they're seeing it in ultraviolet as well. The mantis shrimp has like 20 some cones. Like, it's just insane. If you've ever seen a picture of them, they're very colorful. What percent of your bones are located in your feet? Is it 5%, 10%, 25%, or 100% of your bones located in your feet? %25 of your bones are located in your feet. That's like 12% per foot. The Apollo astronauts couldn't buy life insurance because it was so dangerous. What did they have instead? They signed a lot of autographs. The government provided insurance. A car dealership donated funds, or nothing. They just went for it. Yeah, they were not able to purchase insurance, and so they signed a lot of autographs that in the event of a horrible catastrophe, their families could sell to raise money. Fun-ish fact. Which of the following is the greatest amount? Stars in the Milky Way galaxy, trees on Earth, species of insect, or cells in the human eye? Which of those categories has the most things in it? There are about 3 trillion trees on Earth, which is just a mind-boggling number. Okay, this is our final question. A full fridge is more energy efficient than an empty one. Is that true or false? is true. The air escapes when you open the fridge door. And so the more stuff you have in there, the less air there is to escape. And those solids and liquids keep their temperature a lot better than air does anyway. All right. Congratulations to our players. I hope you enjoyed yourself today. Amaranth Diggums, you get the special paper crown, which will be mailed to you. And we're ready for our next contestants.
Welcome back, everybody. Our next presenter is Rachel Taylor. She's from TuSimple, where she's a map production specialist helping to develop autonomous vehicles. Take it away, Rachel.
Hi, everyone. Thanks for having me talk for this today. I'm really excited. So I'm going to tell you about my journey into robotics through mapping, drones, and self-driving trucks. So I work for a company called TuSimple right now, and I'll tell you a bit more about that later. So I just want to introduce to you first a little bit about who I am, and then I'll talk to you about geographic information systems, which is what I studied and which is what led me into this field of robotics. So I'll also talk about mapping, drones, and robotics, as well as the self-driving freight trucks. So like many of you, I was born and raised in the Mountain State. I'm from Preston County. And, you know, when I was your age, I was a pretty average student. I loved sports. I played soccer and basketball. I ran cross country. I liked nature a lot, always out hiking, playing in the dirt, loved video games also. And I would say my favorite classes were art and science. So I graduated from Preston High School in 2012, and I immediately started college at West Virginia University. And I wasn't really sure what I wanted to go into, but I knew it had to be for science. So I'm also a first-generation college student, which means that nobody else in my family had ever been to college before me. So that was a really exciting time in my life. So I found myself studying recreation, parks, and tourism resources. So of course I got to learn about trees and plants and zip lining and how to be a park ranger. But during that time, I also found research and GIS, which sort of pulled me back into the more scientific side of things. So later after that degree, I did another degree at West Virginia University, and it was for my master's, and I focused on geography and GIS, and that's where I took a class on drones and completely fell in love with the whole idea of it. So you're probably wondering, what is GIS? What is this thing she's talking about? So I like to describe it as mapping software. It's a method of organizing and visualizing your data on a map. So if you think about your house, your school, your favorite place to eat, they all are in different locations, but they're all related to one another. So a GIS map would help you visualize it and see how those things relate. So if you think about a GIS map versus a paper map, it's much more interactive. It's on a computer, you can zoom in, you can, check out all these different features. And the most important part is that you can add additional layers of information. So you're not just looking at one type of thing at any time. So if you think of Google Maps and navigation, you've probably interacted with GIS before. So another example that helps people understand is addresses and 911. So if you've ever called 911 or you've learned about it, you know that the emergency responders ask you for your address. And when I was a kid, I was always so confused how they would know where to go. And it's because of, GIS and maps. So another example I really like is hiking. So if you go out in the woods and you have a trail map, you know how to make your way out. But it's not all just maps. There's so much more to GIS. And like I said earlier, the ability to compare and combine the different layers of information is what really makes it meaningful and allows you to ask deeper questions than just where is something or how to get somewhere. So among other things in GIS, one of my favorite parts of it were aerial imagery. So for aerial imagery, there are many reasons why we would want to look at the Earth's surface from above. Things like land cover. So if you want to see what the surface of the planet looks like, you can look at climate change in this way. So if you see the picture here on the left, it shows the ice cap here. And going back to the layers, when you have two layers together, you can look at something from many years ago, and then you can look at something now. And when you put them on top of each other, you can see the difference, and you can actually quantify how much something has changed and in what ways it's changed. So another way of using aerial imagery would be development planning. So if you want to build a new building or something like that in the city, you would want to see what the area looks like and then be able to visualize how the new building might fit in. So another example is farming and agriculture. So if you have your field of plants and you take some aerial imagery of them, you can really learn a lot from that information. And you can see if there's something wrong with your crops or areas where things are growing better than the other. You can ask many questions through this. So another one that I think is quite relevant to West Virginia is emergency response. So for example, if there's a flood or something, being able to see the ground from above helps us visualize where there are issues, if there's people that need rescuing, and where we can put our resources to help mitigate this emergency. So typically, aerial imagery has been collected using satellites, airplanes, helicopters, things like that. So that brings me back to drones, which I'm very enthusiastic about. And it's been a very cool addition to the world of geography to have drones, because they really help assist in data collection. So compared to launching a satellite or an airplane, drones are cheap and they're quite reliable, and they're a very accessible tool for data collection. I would argue it's a lot easier to learn how to use a drone than to fly an airplane or launch a satellite to get your aerial imagery. And so another great thing about drones is that they're small and you can collect data for more specialized purposes. So at this point, you might be wondering, well, what does this have to do with robotics? So drones are essentially flying robots. There's no pilot on board. And oftentimes when they're flying, they're using pre-programmed flight paths. So this brings me to my master's degree project that I completed at West Virginia University. So I used GIS and drones for mapping. So this is a picture of Prickett's Fort State Park. Some of you might know it. It's located outside of Fairmont, and it's a really cool structure. If you just look at it, it looks like something out of a video game. And so I wanted to see if I could use a drone to collect a bunch of images of the area and create a map of it. So using the drone, I collected hundreds of individual images and used them together to create a 3D map of the fort. So I used an autonomous drone flight to collect this data. So this is a little screenshot of an app that I used called Pix4D. It's really cool for interacting with the drone and helping set up its autonomous flight path. So using this app, I told it the flight location. So I took a little map and scrolled over to it and placed that little yellow box over top of the fort to tell the drone that that's where it needed to fly. And so you can see the little white boxes are the flight path. So that was where the drone needed to fly to take its individual photos that I would later stitch together. So using this app, you could also change the altitude at which the drone flew, so it wasn't too high or too low, and you change the speed. So if it's flying too fast, your photos are going to be blurry. And if it's flying too slow, you're probably going to run out of battery before you're done collecting your data. And so you can also change the camera angle. So if you want it to look straight down, or if you want it to look a little sideways towards the things it's taking photos of, you can do that. And then the last setting is for overlap between photos. And it's very important to have a big overlap between each photo, because that's how the software later would go back and stitch it all together. So for that, I used drone to map software. And so you just dump all your photos in it. I think there was 400 photos about. And so I gave it all of my photos, and it uses positional data that was collected by the drone during its autonomous flight. So it's sort of like putting together a puzzle, but imagine all of the pieces already have labels for where they belong and how they fit together. So this is an example of 3 photos that were taken one right after another. As you can see, there's some similar buildings in there, and the drone just sort of flies along, takes a photo, flies along, takes a photo, flies, takes a photo. So all of those combined resulted in something like this. So what you're looking at right now is a top-down image of the fort. And all of the little blue dots are where the drone took a photo, and the orange lines connecting the blue dots show the flight path. So something I want to point out that's really, really cool about the drone's autonomous flight is that it was super windy that day when I collected the data, but somehow the drone was able to correct itself and know that it needed to stay on the path and it needed to fly to the correct places. So here's a better photo without all of the camera places over top of it. So you can see, you know, this was constructed by a ton of tiny little photos. And then another really cool thing that I loved about this process is that you don't just get a photo or an orthomosaic image at the end. The drone is also able to work with the software to extract information about the surface of the Earth. So you can see there's different colors here, and that's to show elevation. So you can see the buildings, and everything within the fort is red because it's a lot higher than the surrounding ground. And then you can see there's sort of a gentle hill over here. And if you look really closely, you can sort of see a sidewalk that goes down away from the fort. And then there's also this little imprint in the ground, which I thought was really fascinating because that was where a garden had been planted a couple years ago. There was no garden there anymore, but the drone was able to extract this information from the aerial imagery. So this is the part of my project that I was especially proud of because, as you can tell, it's no longer a top-down image. It's 3-dimensional. And when I completed this project, it wasn't just a photo like this. You're able to scroll in and zoom in on certain things. You could see all the details in the chimney of the building. You could see the individual logs that make the fence. And so it was really impressive that I was able to get such a realistic 3D representation just from a bunch of tiny little drone photos. So this is the project that helped me earn my master's degree at WVU. And my next step was to go out in the world and find a job. So that's where the autonomous vehicles comes in. So if you think about self-driving cars, it seems like a modern technology. It's very futuristic. But the idea of self-driving cars has been around for over 100 years. And the first version of one, the Stanford cart, came out all the way back in the 70s. And so I found these images and I thought they were really cool. You can see on the top one, it's not a self-driving car. It's a long way from it. It's a little cart and it has a camera at the top of it. So the way it works, it would take a bunch of photos and the camera would move across the thing and it would take all of these photos and then it would have to sit for 10 to 15 minutes and process the photos and then understand what was in them and then make its plan for its next move. So then it would roll forward a little bit, take a bunch of photos, and then take 10 to 15 minutes to plan its next move, and so on and so forth. So the bottom photo shows some of the early experiments they did with it, where they just set chairs and other random obstacles that didn't look very similar and just saw if the little cart could navigate around it. So it was using cameras and a really early version of artificial intelligence. So for this time period, it's super impressive. So in 1979, I believe it finally navigated the entire room without human intervention, and it took 5 hours. So that's not very practical for a self-driving car, but it was a very early version of this technology. So if you fast forward to 2021, we have many versions of self-driving cars already on the market that you can buy and ride in. So of course, they look a lot different now, and it's a long way from the cart. So even today, though, the self-driving cars operate using cameras and artificial intelligence, just much more advanced versions. They are able to recognize stop signs, traffic lights, pedestrians, and many other things that tell the car about the rules of the road. So that brings me to the self-driving freight trucks. So when I say a freight truck, I'm referring to a large truck that delivers cargo between locations. So if you think about produce and other food and packages, mail, electronics, any of those things that you can buy in a store typically have been delivered by a freight truck. So when I left college, I got hired with a technology company that designs and employs self-driving freight trucks. I was honestly very intimidated at first. I thought, how am I qualified for this job with my skill set? I don't know how self-driving cars work. But I quickly realized after I learned about the position that it was a perfect way to combine my knowledge about GIS and mapping and autonomous technology. So now I have a little video that tells you a bit about my company and what we do.
What if technology could change the world for the better? What if we could create a virtual driver who never drinks, never texts, and never gets tired? What if you could transport freight coast to coast in 36 hours? What if you had nearly unlimited freight capacity? What if we could distribute more food and supplies to more people faster? What if you could make trucks more efficient and reduce their carbon footprint? What if you could stabilize and protect supply chains against the unexpected? What if you could lower the cost of freight transportation by 30%? Introducing the TuSimple Autonomous Freight Network, the world's first and only autonomous network, providing greater access to self-driving trucks than ever before. TuSimple's expanding network of mapped routes allow long-haul autonomous trucks to transport freight to facilities across the country, day and night, rain or shine. by creating an ecosystem of L4 self-driving trucks, strategically located terminals, and HD maps. We make it possible for autonomous trucks to operate safely and efficiently in nearly any weather condition. 24 hours a day, 365 days a year. And with our autonomous operations monitoring system, TuSimple Connect, we ensure every truck is where it needs to be when it needs to be there. Giving users the peace of mind that comes with knowing your freight will arrive on time, every time. The TuSimple AFN provides access to reliable autonomous capacity. And with its powerful advantages such as greater efficiency, enhanced safety, lower operating costs, and the valuable insights that come from using TuSimple technology. The TuSimple AFN is an inclusive ecosystem, and by working closely with industry partners, we will scale autonomous service nationwide by 2024. With the launch of TuSimple's fully operational autonomous freight network, we are creating the safest and most effective way to bring autonomous trucks to market. And this is only the beginning. TuSimple. A better path forward.
Okay, so I hope that video made everybody as excited as I feel about my job. So every team at our company is equally important for the performance of the trucks, which is something I didn't even realize when I first came into the job. So between hardware, software, and mapping, everybody is equally important. So for the hardware, think about the people that actually build these trucks and install the sensors and all of this technology that allows the truck to drive on its own. And so then you think about the software, which is the people who design the algorithms that actually drive the truck and teach the truck how to interact with the maps, which the maps is my thing that I do. So they mentioned in the video the autonomous freight network. So what we are building with our maps essentially is all of the popular highways where freight trucks will make deliveries in the US. So a lot of our routes are in Texas and a lot of southern states. We have Texas, Arizona, even places like North Carolina, Florida, Alabama. So we're slowly but surely building this network of roadways where we digitize all of the features of the road so the truck knows what the road is like and it can follow the rules of it. So I like to think of the autonomous freight network sort of like a 5G phone or something. So if you have a 5G phone, but you don't have any 5G phone towers to provide that wavelength for the phone to operate off of, it's just a regular old smartphone. But once you build the 5G network, the phone has that to operate off of. I also like to think of it sort of like the electricity in your house. So if you're staying in a house, you know, maybe a cabin or something that doesn't have electricity running through it, all of your electronics are basically useless because there's no network for them to operate off of that powers them. So the way we build this autonomous freight network is first we choose a new route to map. So we sort of put them in order of importance, where our trucks are actually going to be making deliveries soon and what's next ahead of that. So there's a photo here of a Ford Explorer, and this is what our mapping vehicles look like. So we use these vehicles to drive the route before a truck ever goes near it. So as this vehicle drives the route, it's collecting all of the data that we're going to need to be able to build the roadway as a digital form. So these cars are equipped with LiDAR sensors, which is basically just a lot of really fast laser beams shooting out. And when the laser shoots out and returns off of something, it bounces back to us. It allows us to understand how things relate to our car in space. So that gives us sort of an idea about the three-dimensional structure of the road and the surrounding structures. And then it also collects camera imagery. So next, the data is handed off to my team where we post-process it and we get it ready for people like me, the map production specialists, to digitize all the features of the road. So when I say all of the features, I really mean everything. Everything is planned and figured out logistically to ridiculous level of detail. So speed limits, the shapes of the lanes, exit ramps, entrance ramps, even the paint on the road, traffic lights, all of those things. It's very important that the truck knows its surroundings, because then the technology on the truck will allow it to focus on reacting to other drivers on the highway. So our biggest concern, safety first, always. It's a little interesting to think that there could be giant trucks on the highway that are just driving themselves. And we understand that that's sort of intimidating for any person, not even just the average consumer. So safety first is our number one. And that is why we take so much time in detail to look at these roads and make sure it's accurately reflected for our trucks. So here's a little screenshot, sort of an example of what the drivers on board will look at. So as you can see in the top right, there's a driver in the seat, but he's just there to make sure that the truck is operating as planned. So they get sort of some diagnostics on their tablet in there. So you can see, if you look in the middle, you see the roadway. If you look really closely, you can see the dashed lines in between the highway lanes. And you can see some ramps off to the side. And you can also see these little circles going out from the truck. And that's just showing just how far the truck's sensors reach. It also shows things about the speed limit and the throttle for the acceleration and the brake, as well as the engine brake. So it does operate like a normal freight truck. It's just driving itself. So our trucks are what we call level 4 autonomy, which means the truck drives itself. And it can do it from beginning to end, except in specific scenarios, such as construction zones. I just mentioned safety first. So a construction zone, there's no way that we can map that and guarantee that it won't change by the next day or by the next week. And so this is why we still have drivers in our truck, because they disengage the autonomy and then they drive it manually. So the truck, as I mentioned, can see over half a mile ahead. So that is much further than the human eye can see on the highway. And the computers on board can perform 600 trillion operations per second, allowing the truck to respond 15 times faster than a human possibly could. So our trucks have actually already driven 3.7 million miles and have already made many deliveries. So someday you might get to enjoy some goods that have been delivered by our trucks in the future. So I just want to leave you with some closing thoughts. If you can't tell, I'm very enthusiastic about science. Science is cool. Stick with science, kids. Never stop being curious about the world around you. Anything that you encounter that you don't understand is simply an opportunity to learn. And just because your path isn't a straight shot from point A to point B, trust in the process. I mean, I started college studying trees and leaves and the outdoors, and now I'm working in a field of robotics and absolutely loving it. So applications of robotics are everywhere. And I'm just curious and wanting you to sort of think, what role do you expect robotics to play in your life moving forward? Thank you all so much for your time.
crap over and over again.
Hello, everybody, and welcome again to Day in the Park 2021. You may have heard me earlier in the morning introducing some of our other speakers, but we haven't been introduced yet. My name's Ryan Utzman, and I'm the STEM competitions lead for the NASA IV&V Program's Education Resource Center. Before I start my full-on presentation and slideshow, though, I'm going to talk a little bit about the ERC and what we do. So the IV&V program, the Independent Verification and Validation Program, essentially checks all of the software that NASA needs for all of its missions. In addition to that primary function, the IV&V program also supports the Education Resource Center, which, as you can see from our website there, is also a partnership with Fairmont State University. And the ERC, through a number of different initiatives, has the goal of inspiring and engaging youth to have a positive impact on their communities and to choose to pursue STEM careers, ideally at NASA in the future. And so we have a few different approaches to doing that, including events like Day in the Park. We provide training for formal and informal educators, so your teachers, homeschool co-op coordinators, scout leaders, 4-H leaders, things like that. We have a whole suite of equipment that we loan out to these folks once we train them so that they can use them in their classrooms, in their meetings, etc. And again, give all you students access to some high quality STEM education programs. We help to support internships and national service organizations, be those through the official NASA internship portal or through partnerships with other organizations like the West Virginia Space Grant Consortium or AmeriCorps and its VISTA program. And then my focus is on STEM competitions. So the idea behind supporting these STEM competitions is that all of you kids out there who are interested in science and math will see these competitions, be inspired and excited by them, and want to try them out, and by doing so, decide to pursue those careers in the future. So I'm going to spend the next several minutes talking about all of the different STEM competitions that we support that middle school students like you can engage in right now, and high school level programs that you'll grow into in the next couple of years. And then when I have it, we'll watch some video of actual gameplay. So let's jump right into our first set of programs, and fittingly, those are called the FIRST programs. In this case, it's an acronym for the Inspiration and Recognition of Science and Technology. FIRST is a nonprofit that was founded, just about 30 years ago in New Hampshire by inventor Dean Kamen to do all of those things I've already laid out, get kids some hands-on STEM experience in a fun, exciting, educational way. First, LEGO League is where we'll start. As you can probably guess from the title, the robots are made out of Legos, and you can see on that image to the right, the thumbnail of the video I'm going to play shortly, that the robots have to drive around this field and complete different tasks to earn certain amounts of points. Now, these robots have to perform completely autonomously. Once it leaves that little semicircle in the right corner there where you can see it's set up, it can't interact with people until it returns. So similar to the Mars rovers or other autonomous robotic vehicles, once they leave the human's hands, they have to figure it out for themselves, similar to what Nick spoke about in his presentation earlier. In addition to the robot side of things, First LEGO League teams also have to do a research project where they find a problem in their community and solve it by creating some invention or engaging with members of the community. So without further ado, I will hit play on this video and we'll take a look at our, I believe this was our state championship run from last year. So this is a team from Parkersburg, score 390 points. And they're off. So they hit go when the timer started, move forward and dropped that white Lego payload next to the park bench. And now they're going to go to this near corner. They drop something into the bucket and then lift the bucket up. Almost took it all the way off the top, but they set it back down and back away. They're going to flick this red block. Now I believe they back up into home base. So now that it's back in that home base area, students can swap out attachments, pick the next program in their sequence, make sure everything's lined up, and then they hit go and it goes off to complete some more tasks. I've got the sound turned off for all of our videos today just because there's copyrighted music and stuff that it would be a headache to deal with on the stream later on. But there's a lot of intense cheering going on in the background. You can see the signs twirling. Obviously, the past 1 to 2 seasons of robotics competitions have been a little bit different from normal. Normally, these kinds of events would happen in a large gym. There'd be 12 to 24 teams, lots of excited parents and siblings, and more people with signs cheering them on, music blaring in the background, trying to make a fun, exciting environment. Now they're off again on their third mission. They're going to pull this person, help them down the slide. Ooh, looks like they brought 2 down the slide, and then they're going to bring them back to home base for some extra points. And they do just get completely inside of the circle before they touch the robot again. One of the common threads across all of these programs is that they release a new game every year. And so for First LEGO League, the obstacles in the table change to provide a new challenge. So you can't just keep running the same robot year after year after year. On this particular mission, I think this is the second to last one they do, there's a plunger you had to push in, but it had a ratchet attached to it. So you couldn't just slide it through. You had to bump it a little bit every single time. And they had the little dance moves picked out for everything the robot did. They've dropped all of those cubes into the goal, and they wrap up their mission by dancing on the target zone. And so that is the robot side, at least, of First LEGO League. As I mentioned, teams also have to do some community outreach aspects, and then they have to put all of their technical achievements and their research project into a series of presentations that they share with judges. First LEGO League was at one time the largest program in the state with over 100 teams across West Virginia. Things have obviously slowed down a bit over the past couple of years, but we're hoping to see a resurgence right now. Most of the teams are concentrated in north central West Virginia with a couple of outlying pockets towards Parkersburg and out near the end of the eastern panhandle, but we have competitions all over the state. So it's a great time to jump in if you're interested. That brings us to our next program, First Tech Challenge. This is a middle and high school program. There's a lot of heavy competition. The robots, as you can see from that thumbnail on the right, are not made out of Lego. The construction rules are pretty wide open. I know one of our teams in West Virginia last year worked from a garage that had some woodworking tools in it, and they made their robot almost entirely out of wood. Excuse me. But it also opens up the door for other advanced manufacturing. If you go to a school that has a machine shop from a tech ed class, there's some opportunity to work some metal in there. And on the software side of things, these robots are both autonomous and teleoperated, or driver controlled. And the way that is set up is that the game pads that you use to control the robots, just like a video game, talk to the robot's brain, which is basically a rehoused Android phone. And so by learning how to program that communication, you also develop some skills in developing on the Android platform, which is quite widespread. As I mentioned, these games are a combination of autonomous and driver controlled. And to make things more interesting, you can see from that thumbnail once again, there are multiple robots on the field at a time. And so these matches are set up 2v2. So I'll go ahead and get this video started and add some more information as we go. I think this is the one program where I didn't have a video handy with teams from West Virginia, but this black robot in the back here, 8393, they're from Pittsburgh. They compete at our event locally every year that we have it. And this is footage of them playing in the final match for the World Championship. So still a lot of high stakes. There they are on the right, extending that elevator out. So this year's game was themed around the moon landing. In the middle, they had a moon lander, and the robots have to start attached to it, and then they deploy into the game field. And then they have to collect artifacts and return them to the lander there in the middle. That first segment that we just wrapped up was the autonomous period, and now the robots are under driver control. So they're going to continue scooping up those artifacts, dumping them into the lander. We've got 2 blue teams and 2 red teams, so they're trying to score on their respective sides. And then at the end, in the last 15 to 20 seconds or so in this particular match, they're going to latch back onto that lander and try and lift themselves back up to score the maximum amount of points. As you can see, they've sorted those moon artifacts quite effectively. One side of blue and one side of red is for the wiffle balls, and one side is for the cubes. So the robots have some sensors inside that allow them to realize which game piece they have and dump it in the proper spot. There's a lot of automation there, even though this is technically driver controlled. In this particular setting, because they're playing for the World Championship, they've picked their partners. But for most First Tech Challenge matches, you get paired with random partners and opponents. So you have to build a well-rounded robot that does a little bit of everything and works well with others. Because you might, if you end up building a robot that does the same thing as your partners, you may not maximize your score. Now we're reaching the end of the match. You can see at the bottom, blue has the lead for now with about 15 seconds left, and the teams are going to approach the lander and try and latch on and lift up. Got that robot on the left that says bros on the side of it, clearly off the ground. Their opponents on the left side now also hanging. And then this robot in the middle couldn't quite make it in time, but that's the match. And that is First Tech Challenge very quickly. In addition to the robot side of things, teams are judged based on a technical interview. So they have to describe to the judges the cool, neat features of their robot that help them play the game effectively. And they have to document how they build their robot. So all of the brainstorming, all of the testing they did, all of the improvements and changes they made throughout the season. That brings us to the final and the original first program, the first robotics competition, which is an incredibly fitting name. This is kind of the progenitor of all educational robotics programs. The robots, as you can see here on the left, are quite a bit bigger. In a typical year, they are, this one that's pictured is about 2 feet by 2.5 feet wide and just under 6 feet tall. And it weighs 120 pounds, including a 15-pound battery. It had a top speed of just under 15 miles an hour. And from the video we're going to watch here on the right, there we go. We can see that these games are played on a huge field. This particular event was at the WVU Rec Center in the summer of 2018. So that field's just about the size of half a basketball court. It's 27 by 54. You can see there are 6 robots, 3 red, 3 blue. That first section, again, was autonomous, and then they moved to the driver-controlled program. For this particular game, we had 3 teeter-totters with red or blue lights around either side, and you had to use the cubes to tip the seesaws in your favor, and for every second that you controlled it, your team earned a point. So those scores at the top are going to go up and up and up automatically as the teeter-totters balance. So I mentioned as pictured on the left, that robot's just under 6 feet tall, but we can see it kind of right of center of the video now, moving to the bottom of the field and raising up. It had a height of just about 13 feet. One of the other, in addition to the size and scale of everything in FRC, one of the other key differences between this and other programs is that FRC encourages partnership between students and adults. And so where the other programs are pretty focused solely on students, on an FRC team, the students work alongside professionals. So Nick, that you met earlier, and I mentor the team that we're watching right now from Morgantown. We work with students and their parents who are lawyers and professionals and arborists and woodworkers. Any skill that they have that they can help transfer on to the kids is welcome. And most other teams operate the same way. There are only 4 teams in West Virginia right now, in Morgantown, Parkersburg, Eleanor, and Chapmanville. But we're always looking to add more. It's a pretty exciting, if expensive, competition to run. And every 2 years, when the world is normal, every 2 years at the rec center, we run an off-season event that lasts for 26 hours and 14 minutes. So we start at Friday afternoon. We play all through the night with matches nonstop and robots running constantly until 2 p.m. or so the next day. So that is a very quick overview of FRC. And now we'll move on to the VEX family of programs. Starting with the VEX IQ Challenge, it's for elementary and middle school students. It is a Lego-like platform. There are plastic pieces that snap together. Similar to FTC and FRC, though, the games are played with multiple robots on the field. There is a combination of driver-controlled and programming aspects. And similar to FTC, teams keep an engineering notebook and get judged on their technical skills with an interview for referees. So let's take a look at this match from 2 years ago at this point. This was taken from a tournament at Ripley High School. Team is Rocket from Huntington. All right, these matches are only 1 minute long each, so there's less to do than on the Lego League field, but it's a little more challenging to do it. You saw just there, they switched drivers. Teams have to switch drivers halfway through the match to encourage teamwork. But in this particular game, they had to move the cubes to the proper colored area, green up on the platforms, red and blue to their respective corners, and then they got additional points for placing the balls into or on top of those cubes. Similar to the other programs, teams get paired with random partners, and you have to work together to maximize your score, and then teams get ranked based on their average score, and the top teams get paired up for the playoffs. That's VEX IQ. It is currently the largest program in the state, just under 200 teams in the last normal season. We expect that to bubble up just like it was before. Those teams are pretty widespread around the state. There's a huge concentration in Kanawha County. Huntington has a huge population as well. Clusters are in Parkersburg, Elkins, Buchanan area, and again out in tip of the Eastern Panhandle near Martinsburg. But again, looking to grow all of our programs all over the state. So just because you're not in those areas doesn't mean you don't have a team near you or that you can't have a team near you soon. That brings us to the VEX robotics competition. Again, this is middle and high school, similar to FTC. As you'll see when we watch the match in a few minutes, the game is played on a similar sized field. The robots are a similar size. The build rules for VEX robotics competition are much more restricted. You have to use VEX parts, which are kind of like an erector set, which I assume most of you middle school students haven't actually seen in person now that I've said it out loud, so probably not the best analogy. But because you're restricted in the parts you can use, you have to there's a lot more room for forced creativity to make your robot do what you want it to do. Similar to FTC, it's 2v2 matches with autonomous and driver-controlled portions. There are further autonomous and driver skills challenges available, and again, teams are judged on interviews and an engineering notebook with their process. Let's go ahead and check out this match from our last in-person event. Took this in Charleston. On the red side of the field on the left, we have Ripley High School and Sissonville. They're going up against Brook High School and Riverside on the right in blue. This year's game, as we'll see when the graphics pop up here in a minute, is similar to tic-tac-toe. So you're trying to score your colored balls into the goals, but then the ball on top will determine if the goal is red or blue. You get bonus points for completing rows, just like tic-tac-toe. The VEX Robotics platform that they use for the VEX Robotics competition is also used by a number of other organizations. And so one of the reasons it's grown so much, it's the largest high school program with just under 125 teams in the state pre-pandemic. One of the things that has encouraged that growth is that other programs use the VEX parts and electronics and programming to run their own competitions or their own educational programs. So some schools participate in Project Lead the Way. Their engineering courses use the VEX platform for their curriculum to learn about intro to engineering, basic machines, gear ratios, things like that. It's also used with its game by TSA, Technology Student Association, and JROTC in some places. Over the past, as this match winds down, with 20 seconds left, over the past 5 to 6 years, some folks locally have been trying to leverage the ubiquity of the platform to convince the WVSSAC, the Secondary Schools and Activities Commission, to recognize robotics as a sport or activity. That hasn't happened quite yet, but keep your eyes on the news, and by the time you all make it to high school, you may be able to get a varsity letter in robotics. Keep an eye on the news over the next couple of weeks maybe, and see if any developments pop up on that. And a couple of other programs also use the VEX platform that we'll talk about in a little bit. Next up, we have VEX University. VEX University is basically a rehash of the VRC program. 2v2, it's the same game year to year, but the robot construction rules are more open, similar to FTC. There's 3D printing and advanced manufacturing techniques are allowed. You can use a wider variety of materials and parts. Programming and sensors are wide open for teams to really explore that space at the university level. And instead of just building one robot and getting paired with a random partner, schools build at least 2 robots and field both of them in the match. So instead of being, like we saw in the last match, Ripley and Sissonville against Brook and Riverside, a VEX University match is, for example, WVU and their 2 robots versus Marshall and their 2 robots. I bring those 2 up because WVU, Marshall, Fairmont State, WVU Tech, Shepherdstown, at various points in the past few years. Bridge Valley Community and Technical College in Charleston, South Charleston, sorry. All of those schools have had VEX University teams over the past 4 or 5 years. And again, as we hopefully move to a more normal time, those teams will be coming back into action. So a few years down the line, maybe check to see if your school of choice has a VEX University team to get involved with. We also support a couple of virtual programs. The first one I want to talk about is Zero Robotics, another very fitting name. The Zero Robotics program takes place almost entirely on a browser-based simulator. So they come out with a new game every year, and with it, they release a link on their website that you can go to and program a virtual drone to float around in zero gravity and complete the challenge and score points. From there, teams that score highly on the simulator compete against other teams in their region. So all of our West Virginia teams compete for the highest score on the simulator against each other until our champion is crowned. Once we have a state champion, all of the teams in the state kind of bond together to support that champion and help them improve their code even more, because at the championship event, all of the states and countries that participate compete against each other on real robots on the International Space Station, which you can see in this picture here. Over the past decade, West Virginia has won the World Championship of Zero Robotics 4 times. Got 2 high school championships out of South Charleston High School and 2 middle school state championships from Learning Options, a homeschool co-op out of Bridgeport. Zero Robotics kind of had a timely hiatus during the pandemic, even though they're a virtual program, because the robots on the International Space Station had gotten too old and they weren't performing well enough to keep things going. So they brought them down and they've replaced them with new drones. And hopefully that program will be back in action soon, because I think it's pretty cool. You get to upload your code to the International Space Station and astronauts referee the matches. It's super cool. Next up is a newer program, that's Cyber Robotics Coding Competition. It is similarly browser-based. It's a simulator that simulates the Lego robots that we talked about earlier. They're changing the format here a bit as we come out of the pandemic, but the way it used to work is that there were these different challenges. You could complete them at your own pace, and once you competed against other folks at your school, and the top few scorers from each school got invited to the state championship. At that championship event, it was in person, but still based on the browser. There we go. And so it took place in a computer lab. We'd get everybody from all of the schools in one place, and they'd release some new, much more challenging challenges where you had to complete them under a certain time limit to earn points for your school, and the top earning school won the championship. But again, they're rebooting that competition structure over the next couple of semesters. And then we have some other in-person programs that didn't really fit into the other categories, so I've put them all together here at the end so they weren't left out. First is World Robotics Olympiad. It is a Lego robot base. The challenges are much more technically demanding, but it is similar to First Lego League in that you have to move things around a field. The challenge is, again, much more difficult, much more programming intensive. You have to get a little bit into, to do well at least, you have to have some pretty creative builds, and you have to get into kind of the state machine thing that Nick was talking about in his presentation earlier. Very challenging, but very rewarding. A couple of years ago, we hosted the national championships here in Fairmont. They've moved out to California, but they're looking at their options moving forward. But teams compete locally, advance to the national championship, and from there they can qualify to represent the United States at the World Robotics Olympiad. That moves around year to year. I think most recently, you know what? It's completely left me. I'm not gonna guess a country and be wrong. But it has moved across a number of different countries over the past few years, and it would be really exciting to have a team from West Virginia represent us there. Skills USA is a larger program for career and technical education centers. So every county has some access. I assume that every county has access to a CTE school of some sort. And they have a wide variety of disciplines. There are cooking competitions and welding competitions and car repair competitions. We help support the 2 robotics competitions. The first one is mobile robotics. You can see it at the bottom here. They use the VEX game from that year and then rearrange it into a kind of industrial simulation setting. So in this lower picture, those cubes in the original VEX game for that year, you essentially had to put them in one giant stack and try to get as high as you can. And there were some other ways to score points if you were hanging in different areas at the end of the match, et cetera, et cetera. In the Skills USA version of this game, they repurposed those cubes into crates and boxes, and you had to develop a robot that could sort out the warehouse and things along those lines. In the top picture, we have Urban Search and Rescue, where you have to take a robot, drive it by camera only, so you can see the students sitting at the table in the back there have their backs to the robot. You have to drive this robot by camera around the playing field and find mock bombs. They're really just little wooden blocks that are painted red, but you have to find bombs by camera and remove them to a safe place. And then in addition to the scores on the field, those get combined, again, with interviews and documentation to share what you've learned with the judges to determine the winner. Now we're going to completely leave the land of robotics and talk about a couple of competitions. You'll hear more about these, I think, on Thursday's presentations. First, the America Rocketry Challenge. Teams design model rockets to deliver payloads, and there's a target altitude. The closer to that altitude you get, the more points you get, and you get points for landing as close to your launch spot as possible. So there's a lot of simulation and design work to be done there, and our teams typically do pretty well, nationally speaking. I mean, I could say that for all of our competitions. All of our robotics teams as well compete really tough locally, and then when they move on to national and world championships later on in the school year, they always represent us really well. And then, I think this is the final video I have prepared, the final program I'm going to talk about, and again, you'll hear more about this program on Thursday, the REC Foundation Aerial Drone Competition, or RAD. Teams use these small stock drones. You can see one in the picture in the bottom left, and then they can design different attachments and add-ons to them to help play the game. There is a browser-based alternative if meeting in person is untenable, but similarly to the VEX programs, there are teleoperated and autonomous matches depending on what happens. It's 2v2 on a larger field. I think this year's field is 24 by 24 feet. And there are 2 drones on each side. They can interact with each other, although they shouldn't. And they have a head-to-head game. So let's watch a match here from our first RADC event. We took this video from an event in the Huntington Airport. We had teams from all over the state and also Mississippi for whatever reason. We apparently had the closest event to them in Huntington, so they drove up for that. In this particular game, they got points for passing through the rings and releasing those ping pong balls by using the downdraft from their propellers. Prop wash. If they did that in the first few seconds of the match, they got a massive amount of points. And then for the rest of the match, they had to avoid obstacles like those arches out in the middle and herd the ping pong balls into the corner goals. There are white and orange ping pong balls worth different amounts of points depending on which goal they were placed in. This event went really well. We're pretty excited for the upcoming season. They took pictures and video from this event to use in the release of this year's game, which just came out about 3 weeks ago. It's a bit of a newer program, so the team count worldwide is relatively small. Last time I checked, there are just over 50 teams in the world, and 17 of them are in West Virginia. So, and we are expecting more to come online soon. So lots of opportunities there. Again, you'll hear more about RECF aerial drone competition on Thursday. And that ends my formal presentation. We'll switch back to the website here momentarily while I get my bearings. All right, hello again. Hopefully you have enjoyed the first day of Day in the Park 2021. In just a few moments, we'll move over to our closing speaker, Dr. Mirta Martin from Fairmont State University, who has a few words before you go on your way. After she speaks, I'll pop up the schedule for the next couple of days. This is the shortest day of Day in the Park, so the next couple of days will be about an hour longer, so adjust your plans accordingly. And we hope to see you again over the next couple of days.
Hello, and welcome home to Fairmont State. I hope that you have enjoyed learning about NASA and careers in robotics, astronomy, and aerospace. I hope that this day has inspired you to dream of one day working for NASA, or perhaps in another exciting STEM field. But one of the great things about studying STEM disciplines is that you will benefit from this type of learning, even if you don't plan on pursuing a science, technology, engineering, or math career. How's that? Let me tell you. First, studying STEM disciplines develops your critical thinking and your problem-solving skills. And those are skills that will help you no matter what career you dream pursuing. Whether you want to be an artist, a teacher, or a nurse, or perhaps run your very own business, any career you can dream of will require you to solve problems. People that have critical thinking skills and who can innovate will find success. You can find success. Most jobs require some degree of teamwork, often with a large and diverse group of people. STEM classes usually involve projects and assignments that require collaboration, as you might work with a team that actively develops interpersonal and collaboration skills. And these skills, well, you can use them in any career. Another benefit of studying STEM courses is that they teach you how to manage projects. Because technology and engineering courses often involve hands-on projects, you will learn how to plan, how to break larger projects into smaller steps, and how to manage your time. Again, these are skills that will be so useful to you in any career dream that you may have. You know, the global pandemic has changed the way that we learn, and it has changed also the way that we work. Over the past year and a half, you have had to use technology as part of your learning, just as many as your parents or guardians have had to use the technology for their own jobs. Many of these changes, like regular teleconferencing and perhaps working from home, they're likely to stick around in some form or another. So it's even much more important at this time for you to learn how to use technology. Whether or not you want to pursue a career in STEM, you can also continue to study STEM fields well after you graduate from high school, in colleges, universities, community colleges, and vocational training schools throughout West Virginia. There has never been a better time to explore an interest in STEM fields. Whether you're interested in robotics, aeronautics, aviation, computer science, energy, or climate studies, STEM fields are constantly forging new paths and they're constantly innovating it. It will be the future STEM professionals like you, who will help solve some of the greatest challenges and shape the future of humanity. If you're interested in pursuing a career in a STEM field, Fairmont State University is a great place to start. Whether you want to jump into a STEM career or go on to graduate study, we welcome you home to Fairmont State. We have several academic programs across the entire spectrum of science, technology, engineering, and mathematics. And we have some very special programs, and some of which are the only type of their kinds in the state. Let me tell you a little bit about a couple of them. For example, one of them is architecture. Fairmont State has the only undergraduate and graduate architecture program in the state. Architecture is a unique STEM field that combines art and science. It is an exciting career for creative thinkers. Another field that combines creativity, art, and science is graphic design technology. Upon graduation, graphic design technology students might find rewarding careers such as graphic designers, web designers, technical illustrators, or desktop publishing artists. Let me yet tell you about another STEM program, a unique program, an exciting program, and that's our aviation program. Fairmont State University offers the only FAA 141 flight school program in the entire state. It is an elite program, it's an exciting program, but you can also find non-flight options like management and traffic controls, and even air security. Come join us, come soar with us. With our computer science degree, you can study to become a computer programmer, systems analyst, software engineer, or even work in cybersecurity. And yes, we also have an MBA program with a cybersecurity track. You might also choose to continue your interest in biology or chemistry for that matter. Fairmont State has the latest cutting-edge scientific instrumentation and equipment right here at Fairmont State with incredible faculty, and you'll get to use that equipment with those faculty as soon as you get here. So join us. Another program where you might get to use sophisticated equipment without kind of waiting your turn is forensics. Our forensic science graduates go directly into workforce, and they often enjoy careers like medical examiners, criminologists, forensic anthropologists, and toxicologists. Mathematics graduates have a world of opportunities in education, finance, manufacturing, cryptography, mathematics. Again, that's the future, and that future lies in you. A degree in one of our 3 engineering programs makes use of your love of mathematics and your love of science. We offer programs in civil engineering technologies, electronic engineering technologies, and mechanical engineering technologies. Let me also tell you another field that is housed in the Department of Engineering Technology, and that's occupational safety, the only one of its kind in the state. Occupational safety is an important field that makes sure that public and workspaces are safe. But you don't need to wait until college to keep enjoying STEM activities. There are dozens of activities and events students can get involved in right now. For example, you could get involved in things like with Skills USA, a national technology competition, or our first Lego League, our VEXIQ robotics drone competitions, the American Rocketry Challenge, or even your school science fair. Fairmont State University is also so very proud to regularly host FES Lego Leagues and robotic competitions. So I look forward to seeing you there. For the teachers listening right now, thank you for joining us today. We urge you to reach out to the NASA Education Resource Center for free training access to millions of dollars of STEM kits via the Learn and Learn program. And also for information on STEP competitions. And also if you have any questions, come and join us. Call us. At Fairmont State, we stand ready to help you. I hope that you enjoyed, all of you, the virtual day in the park, and I invite you to explore Fairmont State University STEM programs and activities, and you can find them at fairmontstate.edu/STEM. Welcome home to Fairmont State. I'm so happy that you're here. Look forward to seeing you in the future. God bless you.